I would like to point to stress a very important point of this elongated flame. You see, as I told you, the velocity in the laboratory frame of the tip is the laminar flame speed relative to the burned gas, which is something which is typically 10 times larger than the laminar flame speed relative to the fresh mixture, which is, and it is multiplied by the elongated parameter, which is, as I told you, in the critical conditions that I am going to explain, about 10. So that the important point is that the propagation speed of the tip is typically 100 times larger than the laminar flame speed relative to the fresh mixture. For example, in hydrogen-oxygen stoichiometric mixture, where the laminar flame speed is typically 9 meters per second relative to the fresh mixture, you may have a flame speed which is maybe not only close to the sound speed, but maybe larger than the sound speed. But so it is clear that the essential thing is the following, is that, okay, relative to the laboratory frame, you can go at a speed for a laminar flame, finger flame, typically close to the sound speed, but the flame structure is still quasi-isomeric. Why? It is because the relative velocity of the flame relative to the gas is the laminar flame speed. And this is what is important to the flame structure, is the relative velocity of the gas relative to the flame. And this is still markedly subsonic. So you have still a markedly subsonic flame, in the sense that is defined a laminar flame speed, propagating in the laboratory frame at a very large velocity. And you see, and this is a very important comment for what I am going to explain at the end of this year, this hour, is that, you know, you cannot have a laminar flame. If a laminar flame propagates fast, very fast, like here, it is because it is pushed from behind by a backflow, what I have called a backflow. This is essential to understand the phenomena. You see, it is because you are pushed, the flame is pushed from behind by this backflow here, that you have a speed, UF, capital UF, of this tip that can be very large. So this is important, this large velocity, because it is going to produce a strong compressible effect in front of the flame. And because the laminar flame speed is highly sensitive to the temperature, a strong compressible effect due to the high velocity, if it changes, I will explain you that later, in that case, could have a dramatic effect on the solution, as I am going to explain you. And for me, this is one of the explanations of DDT mechanism in a laminar regime. And I will give, so let me now, with this keep in mind, I will start by the simple analysis similar to the one developed by Guy Joulin 30 years ago. Now I am going to consider this tip as planar. I will neglect the curvature effect. I will concentrate myself on the tip, consider the flame as quasi-planar, and I treated as a semi-transparent piston propagating at a velocity UF and with a flow and with a flow velocity in behind, which is smaller than the piston velocity. So, and the difference is the laminar flame speed relative to the cold mixture. You know, to understand that, you have to think a little bit by yourself, quietly, because all this problem of the velocity relative to what referential frame is not trivial. In a sense, when you have understood, it will look trivial, but for gaining this information, you need to think by yourself, quietly on your desk, and so on. The problem is not difficult. But no, so now I am going to solve, doing like Guy Joulin. I am working with a planar solution, and the way I can use a planar solution, I will tell you a little bit more later on. It's essentially because the time for the acoustics to equalize in the radius, along the radius, is very short compared to the time that is involved in the process. So you can consider the problem as planar here. This is a great simplification. So now you are in the same configuration as used by, as I explained the hour before, the work developed by Guy Joulin. And that was developed by Grisha Sivashinsky, who, as I told you, who was the only one who understood the importance of this work. 25 years later, it was developed. This is something. This is something. And I told you, maybe I told you that, I don't remember, Grisha Sivashinsky was the one who put my attention to this problem. He told me, you look to the work of Guy Joulin. He did, because as I told you at that time, I was concerned by deflagration. I did not notice the work of Guy Joulin. Now, okay, you do the same thing, and you find again a turning point in the solution, self-similar solution. So you neglect the unsteady effect to begin with between the flame and the leading shock, and you have a turning point exactly in the same way as the initial problem, meaning that above a critical value of the elongation, or this is sigma, here it is called S, okay? There is a slight change of notation. It's not good, but this is S. It could be sigma here. It says above a critical value, there is no steady-state solution. So what happened if there is no steady-state solution? You say, okay, if there is no steady-state, we should have unsteady solution. You know, steady-state solution does not exist, but unsteady should exist. This is a weakness of... now, what I develop is the one-dimensional piston model beyond self-similarity. You know, as I told you, one of the key phenomena of the DDT has been recognized from a long time to be the acceleration of the flame. In the quasi-steady state solution, there is no acceleration. So, in a sense, the analysis is weak, and could be not very relevant for the experiment. It turned that it is relevant. Why? For the following. And now what I did recently is, okay, I want to work beyond the cell familiarity. Yes, I want to take into account the acceleration of the flame. And in that case, if you take into account, if you want to take into account the acceleration, now you have to be back to the analysis of Riemann. Riemann analysis developed the unsteady flow behind an accelerating, ahead the accelerating piston. This is what did behind. So it was unsteady phenomena. So you use the same approximation as Riemann. We are back from 1 century before, and it is important. You know, there are so many good work that have been developed at that time that you should know and you should learn. And this is one of the, let me tell you a comment on that. This is one of the main weakness of the present education system. They forget systematically the fundamental problems that have been solved long ago, because, you know, and this is stupid. So now you use the analysis of Riemann. So now you have because you have an accelerating problem, you have downstream running flame compression waves that are mainly acoustic waves, but there are acoustic waves propagating, driven by the acceleration of the flame, acceleration which is due to the increase of the elongation here. And I will not explain, I will not describe the basic mechanism of the increase of the elongation. This is a very, very difficult problem to understand, and it is, you know, people say, okay, it is simple, the flame is stuck at the wall, and now you have a profile of profile which is not homogeneous. You are going fast in the middle than at the wall, so you stretch. It turns out that the problem is a little bit complicated than that, and I don't want to enter. I don't like to enter in this problem. I did not solve it. Nobody solved it for the moment, but I will take as a fact that sometime this elongation increase. And you will see it cannot increase longer before a transition occurs. All right. What I did to simplify the problem is to say, okay, I know that there is a turning point, so I am going to start close to the turning point. So I am going to start to quasi-steady solution close to my turning point. And in that case, you find out that the turning point due to the beyond the self-similarity due to the acceleration is a little bit higher than the quasi-steady turning point. But you do not change the order of magnitude, and not only, but more important, you do not change the nature of the turning point. That there is no solution, even when you take into account the acceleration beyond a certain flame velocity or a certain elongation. This is not an elongation, or it's beyond a critical elongation. Okay, this is what I say. So, here is I was at that point at the end of the lecture. So this is the model. This is, okay. This is to show you that this backflow, which is an essential point for me for the transition, is well established in experiments. by a group in Poitiers. This is a flame, you know, this is a curved flame, and here are the streamlines. So this is clear that this backflow does exist, and explain why the tip can propagate so fast. Otherwise, with a laminar flame, it would be impossible. You have to push from behind the flame. So, okay, now I go, and as now I told you, finally, even when you take into account this, once again, you are faced to a turning point problem due to a nonlinear equation, not only a strongly nonlinear equation, which is called a transcendental equation because the unknown appears in an exponential and in the power law, which is order 1. Okay, this is. I did something bad. I have to be back. So beyond self-similarity, once again, even beyond self-similarity, there is no more solution, unsteady solution above a critical elongation. This is the main result, which is simple. This is simple. Now, what is a little bit less simple, but not very difficult, is to see, okay, you say, what is going to happen? I start close, I increase, sigma is increasing, and what is going to happen close to this point? This is the question. And so what I consider to begin with is a I can start. Okay. So I just okay. Okay. I just tell you that what to do now is to solve the maybe it will be better. Yes, maybe now to tell you what I did, what you have to do as soon as you take into account the downstream running planar combustion wave in front of the flame produced by the acceleration of the front, you have to be back to Riemann. Riemann told you a simple fact that the temperature close to the piston, Riemann was solving the problem of a piston, but the problem of a semi-transparent piston is the same. It tells you that the flame, the temperature just ahead of the flame, the increase of temperature, relative to an initial time, is simply related to the difference of the flow velocity divided by the sound speed. This is Riemann that I have presented to you at the beginning of the lecture. This is a Riemann work. Now you use the Zeldovich-Frank-Kamineski result, telling you that the flame speed increases exponentially with the temperature. Okay, and now you find once again you find a turning point, telling you that now there is no more dynamical solution. Such dynamical solution I have described here, but it is not a complete dynamical solution. It's a dynamical solution in the sense that I take into account the unsteady flow in front of the flame, but I did not take into account neither the unsteadiness coming from the flow back, burn gas flow, neither from the flame structure, inside the flame structure. So it is a partial dynamical solution, and even, you know, like the fully steady self-similar solution, there is no solution above a critical elongation. Once again, same thing. You know, this is simply because the Riemanns tell you that you do not have to worry about the unsteady NX. Just you have to recall the relation that you have between the temperature on the piston and the flow and the piston velocity. That's all. That's okay. To do that, you have to solve the flow by itself. But okay. So now, what I am going to you can expect something dramatic at this point. You can expect something dramatic. You can be, and in fact, what I am going to explain to you, that there is a finite time singularity of the solution at the turning point. Not exactly at, but around the turning point. Okay. It's not so difficult to anticipate that something wrong is going to appear, something dramatic is going to appear. It's not so difficult to anticipate that. Why? You know, close to this turning point, you have, assuming that you are on the branch, physical branch of the turning point, you should have a quadratic relation between the elongation, sigma, and the laminar flame speed. You know, because the elongation, in a sense, is maximum. It's not maximum, it's good. But you know, when you look to the curvature, when you look to the curve solution, the solution near the turning point. For example, if you look to what is the equation of this quasi-steady of this, this solution UF in terms of sigma, and you reverse that sigma in terms of UF, you have a quadratic form. Now, this is a generic expression that you have around the turning point. Every time you have a turning point, near to the turning point, you are going to have a quadratic relation. Aha. Now, take a derivative just for fun. What is going to occur? So now I am, because the elongation is linear in time, you are going to by this relation to find out that the velocity UF behave like the square root of the temperature, the time where T star is the time to reach the critical elongation. So this is a generic expression around the turning point. Now, Now, take the time derivative. What do you find? There is a divergence in finite time of the acceleration. So the acceleration does not diverge in this picture, but the flame speed the flame does not diverge, but the acceleration of the flame is diverging, because as soon as you have something working like square root of T star minus T, take the derivative, and you will find something like 1 over T, 1 over T star minus T. And this is going to diverge at the critical point. This is a sign that something wrong is going to appear. Divergence in finite time of the acceleration. Okay, so now Okay, in this simple analysis where we take into account only the instability, not the instability, the unsteadiness of the compressible flow ahead of the flames, that's all. Now, what you can do is better, is to look, what about the flow? I have a singularity of the acceleration of the piston, if you like, in a sense. The flame is like a piston. But what about the flow? Go to Riemann. It's not exactly to Riemann. You have to be a little bit more clever than Riemann. In fact, you have to be back to Riemann. And this is very well explained in the Landau book of fluid mechanics, for those who are interested. In fact, it turns out that the flow obeys an equation which is similar to a Burger's equation. Where is Burger? Burger is a quadratic term u du over dx. It's not difficult to solve this problem in the low Mach number limit. That's, because as I told you, the laminar flame speed is still in low Mach number limit, and you obtain this relation from now, you know, you have the flow field, the expression of the flow field when approaching the singularity. Oh, very good. Okay, there is no divergence. Okay. The flow does not diverge. Yes. But what about the gradient of the flow? The gradient of the flow is going to diverge. So you just by this simple analysis, you find out that, you see, this is a typical shape of a compressible wave in front of an accelerating front here. And when you arrive at this point, where the acceleration becomes infinite acceleration, take the space derivative, you have 1 over square root at t equal t star, you at x equal x on the front, x equal xf, you find the divergence of the gradient of the flow. So this is a second information. First information, the acceleration diverge of the flame, but more in, once again, the acceleration, not the flame speed. Once again, and now the flow, not the flow velocity diverge, but the gradient of the flow velocity is diverging. You see, as shown by this picture, here. This is a gradient, and okay, now I can let you anticipate what is going to occur. When the gradient of the velocity diverge, what is going to occur? Nobody? Ah, yes, a shock is going to create. You know, remember when we were studying the formation of the shock? A shock is going to be created. But this shock has not to be confused with the shock you have far ahead. You have a new shock that is going to be created just on the flame. Ah, this could be dramatic. Because this really could explain the DGT. But now you have to do more work to show that. So you anticipate this, what in this paper, in 22, I said, okay, a shock is going to appear maybe inside the flame structure, in addition to the shock that are far ahead. No, I am going on the wrong way. So, as I say, that onset of a shock in the flame structure, does that explain DDT? Why not? But one has to be sure of that. Now, we improve the limitation of this analysis in this neither the flame structure, not the burn gas, nor the burn gas are. The problem is when the acceleration increases, neither the flame structure nor the burn gas flow are going to be in crazy state. So I did not take into account that up to now. So I have to do a fully unsteady analysis for a small elongation rate. I will, what is very important is that the elongation rate is small. You do not need a strong acceleration rate. Why? Because the divergence of the acceleration is due to this curvature, to this turning point. Okay, so even a very small acceleration is going to produce a dramatic effect. Nice mathematical problem. So this is the last paper that I have written just at the end of last year, and they appear at the beginning of this year. Now, what to do now? We have to take into account this unsteady effect that I have neglected inside the flame structure and in the burn, in the flow, in the burn gas flow. And this is, and I will not develop the detail, but just I tell you what is the limit I am using. The first limit I am using is that the elongation rate is smaller than the Mach number is much smaller. The Mach number, the flame Mach number. So don't forget the flame speed in the laboratory frame must be large, but not the laminar burning, the laminar burning velocity, which is still subsonic. And this is why you have a small Mach number approximation to use, which is here. This is not very few people. Let's say, if you realize that, you will make a big step forward. First, the flame speed in the laboratory frame can be large, but the laminar flame speed is still very small compared to the speed of sound. This is because, and so you have to think a little bit with the difference of referential frame. Okay, and here is an asymptotic analysis, so I don't want to enter into the detail, but these analyses are, let's say, asymptotic. The advantage of asymptotic analysis is that they are systematic. There is no uncontrolled approximation. You just control the approximation by the asymptotics. Maybe, so once again, the elongation rate is going to be small. And now the first things to do is to take into account, okay, let me think a little bit. In the question outside, I don't care. This is okay. Okay, these are the details of the calculation, but okay. What I am going to do is first to neglect the unsteady effect inside the flame structure. I am going to add the unsteady effect in the burn gas flow that I have neglected because I have used a backflow which is quasi-instantaneous with a flame shape. Oh, I am going to change that. So okay, I say this is nothing new. Near the turning point is a quadratic. Okay, I have said already that. Now, in order to take into account the unsteady effect behind, I should have to be able to solve the unsteady flow when the elongation increases. This is too much for me and for anybody. This turning flow, because you have a turning flow, the unsteady effect, a systematic study of this is what we call a turning flow, you see, turns. When you increase the elongation, it's not easy to perform. What I did is the following. I first noticed the following, that, you know, the result, the backflow that you obtain here is a sum of the burn gas flow coming from different points of this finger so it should be like an integral. The result here should be an integral on the surface, finger surface. Now, in order to take into account the unsteady effect, I say simply the following. When you increase the length, you are going to increase effectively the result of the integral. But there is a delay that is going to appear, is a delay to propagate the information from any point of the lateral wings of this finger flow to the leading edge. So I introduce now, this is a quasi-phenomenologic analysis, it is not an asymptotic one. I introduce a delay for propagating the information coming from the L's burning, for the burning rate to the tip. So this is the delay that I have introduced. And now I did a step further. I say what is propagating the information? The speed of sound. It should be the speed of sound. So I assume that this delay is associated with the speed of sound. This is not a strong assumption. Could be right. What is a little bit more tricky is that this equation is right. But okay. So when you do that, you end up with, for a slow evolution, you assume that the elongation rate is slow compared to all the time scale in the dynamic. And this is not a big deal, because you are expecting that the dynamic is going to be singular, so to have a very short time scale, okay? So, so it's not a big deal to say that the evolution is this is going to be a small number. So you develop, and if you develop, you obtain now what I call a delayed byflow. You know, the backflow I have used is without this term, and now because of this delay, I have introduced the time derivative of the flame velocity. And this is going to be dramatic because, as I told you, this time derivative is going to be strong. So in a sense, I cannot go further with this expansion. But I will do that just to see what happens. And to make a long story short, the additional mechanism, delay backflow, introduced in the expression expression of the backflow in terms of the burned gas velocity, is a time derivative term that you have here, you know, without this time derivative term, the time you have here is the time that occurring from the, because you assume that the elongation is linear in time. And this is the time, so this is the elongation. This is the time dependence of the elongation, assuming that it is a low rate, so it is linear. You have this. And now the new, all this, the green part, you know already, it was in the previous slide. Now the new part is this time derivative. Now you have an equation, you know, which is a non-autonomous differential equation. Why it is non-autonomous? Because the time appear in the equation, not only the derivative and the solution P, the pressure, because I use the pressure here, because I use the pressure, F is the pressure on the flame. P1 is just the increase of the pressure in the flame. It's written in a non-dimensional way. So, so here is the equation. Okay? This is the equation. This is the additional time, the additional unstudied term, which is small here. Okay? And when you use reduce variable, for example, in order you replace the time by the elongation, by the renormalized elongation sigma, so this sigma is the same as the time. Okay, so without this term, you have for a given time, that is for a given elongation, this is the solution with the curve, with the turning point. This one equals 0. And now, on the right-hand side, you do not have 0. You have a small derivative term. That's all. And when you work close, and this is a key point of the analysis, when you are close to the turning point, the left-hand part can be developed around the turning point, and again, you have the quadratic form that you have here. So you have this quadratic, when equals 0, it is the quadratic equation that I obtain for this solution, for this solution that I have described when you do not take into account the unsteady effects on the burn gas, and now you have this. Now it turns out that this equation, maybe you can remember the Riccati equation. No, Riccati equation is an equation says that What is a Riccati equation? This is simple mathematics. Let's start with a basic equation d over dy over d tau proportional to, let's say, forget about the coefficient, positive coefficient y. This is an exponential growth. It grows exponentially with the time, okay? No problem. This is the solution of that is y tau equal y0 exponential tau. This is okay. Now, you say, okay, the life is not linear all the time. Sometimes the life is non-linear. What will be the difference now if if instead of y, I have y squared? This is a Riccati equation. Do you know how to solve this equation? Yes, you know. You must know. Take a little effort. Do not wait for the solution for me. Just make your brain. You know what you do? You divide by y squared. And now you have 1 here. What is the result of that? The integration is 1 over 2. 1 over y, okay? So the integration should be something like 1 over y, okay? But now if you take into account the fact, no, it's clear that when you arrive at a critical time where this, you must have something like t star minus t. So this is t star typical solution of this equation is what it is. It is a divergence in finite time. You see, this, okay, I will spend some time because if at least you retain this, you know, here, when I plot y in terms of t, I have an exponential. Yes, no. Now, because of the square here, what is going to appear is a singularity at finite time. And you can compute the singularity with the initial condition. You see? Very simple. In fact, most of the mathematics are simple. So now you see that the drama is going to come from this quadratic part here, which is my y square here. All right? And this time, finally, you say, if I have a divergence somewhere, this is going to diverge, and this term is not going to be very important. So you should expect a singularity in finite time with this equation, as based on this, what is called a Riccati equation. So this problem has been solved exactly by not only numerically. You can, if you're interested, you can do that yourself with a small computer. Right? It's very easy. What are you going to find is the following: is that this is the solution in black, the physical solution of the equation with 0 here. Okay. Now, because you have this term, you have a divergence in finite time. This is a finite. This I call that T star. Call it TC. So this equation is a typical equation for the catastrophe theory. It was used recently for the earthquake, for even some strange theory based on the epidemic growth that says that everybody is going to die in finite time, you know. So hopefully it does not occur. We are still alive. And it is developed in many, for example, it is developed in biology, in biology 2, to try to understand how some diseases are going to change of rate. You die suddenly, for example, you know, by certain disease. This is this equation. This equation tells you that if you have a disease satisfying the equation I have written, you are going to die in finite time. It is true that you are all going to die. We are going to die in finite time, but this could be very short. Okay. So okay. So this is to tell you that the poor theoretician I am did not invent invent anything in mathematics. This is already known from a long time, not for a long time, that's not true. You have a good reference because now you see here, yes, I am on time, no? How many time I have? 15 minutes? I should stop now? Okay, 5 minutes. I'll just finish because this is, we are at the heart of the problem now. So I cannot stop here. I will not sleep, you know. So, so you see, this is a reduced equation. dy over dt, y squared, this is the equation that I have written, Riccati. Here you have the time, in addition of that, and it is shown. For example, if you are interested to find the mathematical reference to show the solution, go to this paper here, which is devoted to a physical analysis of the earthquake. That is important for the people living in California, for example, you know. And it turns out that the solution is, here you discovered the Riccati behavior, divergence, and now here this you can develop. This is a perturbation due to this term. Now, what is very important, that small and steady effects, very small and steady effects that I retain have a drastic effect on the diverging solution. Because now it is not only the gradient of the flow which is going to diverge, it is the pressure. The pressure is going to jump with this equation that I have developed that do not take into account the shock formation. Now, what is going to, what you are finding, what you are finding by this very simple analysis, that you are going to have a divergence of the pressure in a finite time. So here now you are sure to obtain the detonation. Okay, so this is the art of a small and steady effect. You know, with this small and steady effect, you only know that the gradient of the velocity is going to diverge. That you are this is a good indication that something is going to happen. But now you are saying more. You are saying, okay, not only but the pressure is going to diverge few times after the critical time. So it is this. So just I can finish. To conclude, what this analysis is going to, this simple analysis, it is simple, that the inner structure of the flame is blown up in finite time by the divergence of the pressure. And the slower the elongation grows, yes, the close to the critical time is a blow-off. You know, this distance varies with the rate of increase of the elongation, the epsilon that I have. No. So I can stop here. So tomorrow I will finish this and start some other topics. Thank you for your attention.